Get to make the announcement.
Ah!
No, chat.
All right, so anyway.
Oh, the exam.
Oh yeah, so, so Chad, if anybody tells you the exam was moved to the Thursday after that because a certain classmate named Corey has been receiving funding to go to a prestigious conference, just laugh at them, ha ha ha, because you know better, ha ha ha. Just kidding, it actually is moved a week later. Okay, there we go. All right. Yeah, and the class
That was
laughs.
so cool.
Well, you will send an email too, right?
Yes. Mhm.
That what I said?
Conductors and electrostatics, so we already talked about two of their properties, if I recall correctly, namely that the electric field's zero everywhere inside of a conductor, because if it wasn't, we wouldn't be electrostatic now, would we? Because charge would be flowing in response to that. So if you can actually have electrostatics with conductors, then the electric field's going to have to be zero inside, because otherwise charge would flow and you wouldn't be in a static situation. And then from that it follows, using Gauss's law, that the charge density is zero everywhere inside the conductor, because the charge density is epsilon naught times the divergence of E, and if E is zero everywhere inside, then the charge density has to be zero inside the conductor as well. And if that's true, then that means this, meaning the fact that the charge density is zero everywhere. This means, this means any net charge has to be on the surface. Nowhere else for it to go. So any net charge on a conductor all goes out to the surface of the conductor. It can't be anywhere inside it if you're in an electrostatic situation. If it's not static, then that's not true. But if it's static, if you're in an equilibrium static situation, any charge has to be sitting on the surface of the conductor, any net charge. And we also have that if E is zero inside the conductor, then if I take the line integral of E between any two points, that's zero. So, yeah, the E dot dl twixt any 2 points in or on the conductor is going to be zero, or in other words, our conductor is an equipotential. Or in other words, every point in and on it is at the same potential. So there's a single V for the entire conductor. And it also has to be true that the electric field is perpendicular to the conductor's surface at every point. Because if here's a conductor surface, suppose the electric field wasn't perpendicular to the surface, and you were a cute little charge at the surface there, then you would say, oh, look at that. I can't move out of the conductor, but on the other hand, if there's a component of the electric field along the surface, cute little charge would flow in response to that component of the electric field. But wait a minute, this is supposed to be electrostatics, which means charges aren't allowed to move around, which means that you can't have that situation. It has to be that the electric field is perpendicular to the surface, because that way there's no component of the electric field along the surface in order to make charges move. So if it's electrostatic, the electric field is perpendicular to the surface at every point. Okay, any questions at this point? Okay. Happiness, joy, all this clearness and light. All right. And another thing that, so those are basically our big points about properties of conductors. And so now let's talk about some consequences here. Remember, drew a picture last time. Here's some blobby conductor. Here is some charge sitting outside the conductor. And since charge is free to flow inside the conductor, then negative charges, assuming this is a positive charge, negative charges are going to want to get close to it, because negative and positive charges just think of nothing better to do than to get near one another. And so negative charge will build up on the side of the conductor facing our outside charge there. Meanwhile, if the conductor has no net charge on it, yes, if there's no net charge on our conductor, then there's going to have to be positive charge distributed on the surface on the far side of the conductor. And the overall positive and negative charge would cancel. The net charge would be 0 if the conductor is uncharged. If the conductor does have a net charge on it, well, then that wouldn't be true. But in general, take a conductor which is electrically neutral overall, put a charge outside of it, the conductor polarizes. In other words, negative charge moves to one side of the conductor, positive charge to the other. So the conductor becomes polarized. And also, there's going to be a force of attraction between Q and the conductor, because, yeah, Q is repelling the charges out here, but it's attracting the charges here, and it's closer to the ones that are attracting it and vice versa. And so a conductor and a charge, they'll naturally tend to draw together. There will be a force between them of attraction, whichever the sign of Q. If this was negative, then this would be positive charge, and it would still be like A that's come together. Okay? Any questions? All right, so that's another fun fact. And yet another fun fact would be, suppose we've got a conductor, and I apparently am wanting a pair right now as far as I can tell. So here's a conductor, and here is some cavity inside the conductor. And here is some charge, let's say plus Q inside, let's say it's some positive charge. Then there is going to be what? Around here, what kind of charge will build up around there? Was that?
Negative charge.
Most certainly negative, because negative charge says, hey, I'd like to be near plus Q there. It'll, in general, you'd expect it to have a greater density closer to the charge than further from it. So if the conductor as a whole is electrically neutral, then on the outer surface of the conductor will lie positive charge, yeah. So draw that in 2 for fun. Now, we can inquire exactly how much negative charge builds up on the surface of that cavity. And it's an easy question to answer, because if I draw a Gaussian surface there, and inquire as to the flux through that Gaussian surface. Well, what's the electric field at all points on that Gaussian surface? 0, because it's inside the conductor, right? So the flux through that surface is 0, which tells us what about the charge enclosed by that surface? Why, it would be 0 as well. So the magnitude of the total amount of charge on the inside of this, on the surface of this cavity, compares how to the charge inside the cavity? That would be equal and opposite, right? In order for there to be no charge enclosed, then the total accumulated charge on the inner surface of this cavity here has to exactly balance the charge inside the cavity. So E dot dA is 0 for a Gaussian surface inside the conductor. So there can't be any enclosed charge, and therefore any cavity in a conductor total surface charge, right, equal to minus the charge inside the cavity. Which also tells you that suppose there was no charge inside that cavity, would any charge accumulate on the surface of that cavity? Well, no, because otherwise you can't have any net charge accumulating on the surface of that cavity. That won't work, right? Because then you have a charge enclosed. And in fact, we'll see from when we look at uniqueness theorems that if you can find a solution to an electrostatic problem that you just make up out of whole cloth, and it works, it has to be the solution. There is no other possibility. So, you could guess that, well, no charge will accumulate on there if there's no charge inside, and you can show, well, yeah, that's really true. You won't get any charge accumulating on there if there's no charge inside the cavity. Okay, any questions? Okay, so let's go over example 2.9. These things always, this one always kind of strikes me as, not literally a miracle. Obviously, it's the laws of physics in action here, but it's surprising. So let's say we've got some spherical conductor, and inside of it we've got some weirdo-shaped cavity. Maybe even weirder here than I had on my drawing in the notes there. And here is some charge plus Q at some arbitrary location inside that cavity. And the question is, what's the electric field outside the conductor? So, the problem is, we've got an uncharged spherical conductor. Plus Q is inside some weirdo-shaped cavity. I guess that's not quite accurate. I don't know of any weirdos who are actually shaped like that, but there's a cavity with a strange shape to it, some arbitrarily shaped cavity there. What is E outside the conductor? That's our question. Okay. Well, first of all, we can speculate, we know that there's going to be negative charge attracted to that cavity surface. And so in general terms, we can draw some little minus signs there to represent the fact that that is the case. So I haven't tried to be terribly accurate as to exactly what the density of the charge is, but I just know there's negative charge accumulated there. And what's the electric field inside the actual conductor itself? 0, right? E is 0 inside the conductor. And we say, could it be that this negative charge arranges itself so that it by itself perfectly cancels the electric field due to plus Q inside the conductor? Could that happen? And the answer is yes, because notice that I could make this conductor be as big as I like. I could make it 50 miles across if I wanted to. I could make it 5 million miles across if I wanted to. I could make it infinity across. No, I couldn't. There's not that much metal in the universe. But still, in principle, you can make this thing as big as you like, such that any surface charge can't possibly be having an effect anymore. The surface charge will be so far away that its electric field can't possibly be important. And yet it would still be true that the electric field inside the conductor was everywhere 0. So from that we argue that the surface charge on the cavity itself is able to arrange itself so that it completely cancels inside the conductor the electric field of plus Q. So when I add up the electric fields of the induced surface charge, this negative charge, and the electric field of plus Q, they completely cancel one another. So do you buy that argument? Are you okay with that? Should I say it again? Or what's the story with that? Happiness and joy? Looking for signs of happiness and joy, or at least a lack of despondency.
Corey looks really happy.
Yeah, he does, yes. But Corey always looks sunny and cheerful, so it's hard to tell with Corey. You can't read his expression that way. So, okay. So that's the argument here. Charge induced on the cavity wall. Actually, neither Corey nor I is going to look very sunny and cheerful if the Bengals keep playing like they did play.
I have a little.
I mean, even the Browns.
I have a
Well, see, the Browns need to lose because that way the Bengals will still be the one shown on television. I don't really hate the Browns per se. It's just that they annoy me by, sometimes being on television when the Bengals do. So this is my problem with the Browns
See,
winning. Is
you
if
need
the
to
Browns
have-
have a good season, I never
But
see
see,
the
you
Bengals.
need to have the better team.
What?
You need to have the better team on television, so.
Yeah, I know, right?
So that's
I
why.
don't even know, I never see the Bengal games.
Browns.
Unless
Okay,
they're
it'll
like,
still be on who you play against.
What's that?
It'll still be on who you play against.
When you play against, that's right, yes. Charge induced on the cavity wall.
like the Browns.
So that's our argument, that the induced charge by itself should be able to cancel out the electric field of E inside of Q, of plus Q, inside the conductor. And our argument is we could make that conductor of arbitrary radius. Arbitrarily far away, so its charge can't matter. Yes. So that'll work. But then if you think about it then, well, that would mean that it's actually canceling it not just inside the conductor, but really everywhere, because we could make the conductor of arbitrary radius. And again, we're going to prove a uniqueness theorem, which will ensure us that if we can think of some solution that works, it's the only possibility. That's the great thing about a uniqueness theorem, is that it means that if you can dream up some solution, it is the solution. There's no other possibilities, which is a great trick to have in your bag of tricks. And it rewards cleverness, and I like things that reward cleverness. Now, of course, if you're a mathematician, you obsess over proving that a solution exists, and then you're done. Who cares about actually finding the solution? I just want to know if one exists. But we're physicists, so we just assume the solution exists, and then we find one. I didn't know. So, all right. What charge is induced on the outer surface of this conductor?
Positive.
It's positive, and how big is it? It's Q, right? Because this has to be, the total charge on the inner conductor surface here has to be minus Q. We just showed that. And the conductor is uncharged, it's electrically neutral. So if minus Q is sitting on the cavity surface, then plus Q has to be sitting on the outer surface. So total charge plus Q must be distributed on the outer surface. Right? It's minus Q sitting on the cavity surface, and our conductor is neutral, plus Q sitting on the outer surface. But wait a minute. We just said that the charge on the inner surface of this cavity here, on the surface of the cavity, completely cancels the electric field of plus Q. So given that, how's this charge going to distribute itself on the outer surface? In other words, this charge on the outer surface doesn't even know that plus Q exists in there because the field has been completely canceled. That being the case, how's it going to distribute itself? What's that? Evenly, yeah. It's going to, just by symmetry, it's going to distribute itself evenly over the surface. It doesn't even know, quote unquote, that plus Q and the cavity surface charge exist, so it must distribute itself evenly. So it'll distribute itself uniformly over this surface. So now we've got a uniformly charged spherical shell. What is the field outside of a uniformly charged spherical shell? Yeah, right. It's just like it would be for a point charge at the center of the sphere. So, outside, then, the electric field, if here's the center of the sphere and here's some distance r away from it, the electric field points radially outwards, and E is equal to then Q over 4 pi epsilon naught r squared times r hat. Just like it would be for a point charge plus Q at the center. That's a pretty remarkable result, basically. That, notice it's independent of the shape of this cavity inside. It's independent of where plus Q is inside that cavity. The conductor has the effect of making it to the outside world look as though all you've got is a point charge Q located at the center of the conductor. Amazing. It's a miracle, except it's not really a miracle because it's just the laws of physics, but still, wow. That's one of those things, I get it, and yet it still feels like a miracle to me. So, my train just derailed, my train of thought just derailed. So, and then he was about to say something. So, what was I going to say? I hate it when that happens. You read my mind, what was I going to say? No, not this time? No. Oh, well. I could, well, no, because I'm not always going to say something based on my notes.
Yeah.
Oh, yeah, now I know. That actually did help. Thanks, Steph. Okay. What's the electric field inside due to that uniformly discharged, just the distributed surface charge? 0, right? If you're inside of the spherical shell, it doesn't give any electric field. So in other words, this doesn't contaminate, so to speak, our earlier conclusion. This has no influence inside the conductor. And again, as we will soon see, there is a uniqueness theorem, which says that if you dream up a solution and it works, it's the only possibility. So we dreamed up a solution and it worked, and therefore it's the only possibility. In other words, now we didn't, we haven't solved for the detailed distribution of charge on the inner surface of this conductor. So in that sense, we don't have a complete solution here. But on the other hand, we know that if we made this sphere of arbitrarily large radius, it's still going to be true that the electric field is 0 inside of it. And so there's going to be some way to distribute surface charge on here to cancel the electric field of plus Q. Otherwise, we haven't really proved that there is a solution that works. But on the other hand, since it's physics, there must be something that works because it is physics, and so the world works. So on the hypothesis that the world actually does work, and that, you know, this is a valid theory in some limit, then it should be true there's some way to distribute charge to cancel out the electric field inside the conductor. Otherwise, electrostatics wouldn't work with conductors, but we do experiments and it does, and so we haven't proved that every configuration has a solution. But then again, you know, the world would not work if that weren't the case, so to speak, or it would work differently from how we think. So we assume that there is a way to distribute charge on the cavity here that will cancel the electric field at plus Q. We haven't proved that, but it ought to be possible because it is a conductor and we know there's no field inside a conductor. So if that can be done, then it follows from that that this charge on the outer surface is going to distribute itself uniformly because it doesn't even know of the existence of plus Q in this surface charge because there's no electric field there.
Couldn't we have already assumed though, like, I mean, if you're supposed to be zero inside anyways, and all you're doing is introducing a little plus Q, that it was going to act just like a little plus Q, isn't it?
Well, how do you know that moving plus Q around wouldn't affect the electric field outside? I mean, in other words, it's not obvious to me just initially that this is going to work out this way. Initially, I would have guessed that if I move plus Q over here, it'll induce extra negative charge over here, and that'll make the positive charge want to build up more near that negative charge. You know, your intuition might at first suggest to you that where you put plus Q matters, especially if you consider a situation like, okay, I can make this, you know, microns thin. This thing could be a mile across. I could have a cavity where there's 1 micron of thickness of conductor between this inner cavity surface and the outer surface of the conductor, and I put a charge 1 micron from right there. This thing is 10 miles across, let's say, I don't remember what I said, 10 miles across. It still acts like, to the outside world, that there's a charge 5 miles away from there at the center. The electric field right here is no different from the electric field over here, even though this is 2 microns from the charge and this is 10 miles from the charge or whatever. So it's not, you know, from that standpoint, to me, it's not immediately obvious that this is going to drop out like this. And yet we make this argument and realize that it is. But then you ask yourself, wait, but I came up with a plausible solution. Is it unique, or might there be more than one configuration that would work? The answer is, there's never more than one configuration that would work. If you find a configuration that works, there's no other possibilities. There's a uniqueness theorem which says if you can think of a solution that works, it is the solution. There's no other possibilities that you're not thinking of. So often you can solve these problems just using your intuition, basically. If your intuition leads you to a good guess that works, congratulations, you've solved the problem. You can stop thinking. And much as we all enjoy thinking, you know, sometimes you just want to stop. So, okay. All right. Any other questions? All right. Another fun fact about conductors. If there's no charge inside of a cavity, the electric field is 0 inside that cavity. Okay, there's my gingerbread man cavity. It's like a 70s thing. I had shirts back in the 70s that kind of had patterns on them like this. But
Do you have long hair too?
lovely wife is thinking, stop talking about the 70s. Don't give me that look.
Yeah, he had long hair too.
Yeah, I did. That's right.
How
Yeah.
long? Did you have a ponytail?
I never had a ponytail,
Did you have
no.
a
But
mullet?
when I look at only once by accident. That was when I was in Virginia as a professor and went to a barber shop at a mall. And I guess the guy just looked at me and decided, mullet. Because I walk out of the, you know, I just looked at myself in the mirror from the front. I said, oh, that looks fine. I walk out, lovely wife to say, if you looked at your hair in the back and oh my God, it's kind of like this in the front, it's like down the hair. So, no, 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 I don't drive a pickup truck. And so,
I think you just offended Chad.
I probably did, that's right, yes. Not that I have anything against people that drive pickup trucks, believe me.
No,
But-
he listens to country music.
Yeah.
He does listen to country music.
Right.
E equals
Right.
price.
So we had to go and get that fixed. And I mean, the guy who did my hair, he would never wear a mullet. I mean, he was kind of like, you know, think of a guy who likes to cut both men's and women's hair, and this is what he was, and you know. I mean, he was like
He
a,
was just
you know,
experimenting.
he was a hair artiste, as it were.
Artiste.
But somehow he gave me a mullet, and I don't, you know, I just didn't get that, because
It
he didn't
wasn't-
seem like a mullet
See, he
inducing
didn't
kind
call
of
it
guy,
that,
you know.
He called it
Right. What?
He didn't call it a mullet, he called it moulet.
He called it a moulet, that's right, yes. I had a lovely
Dude, I need a
moulet.
relay.
Right, yes,
Very nice.
right. So, yeah, but you know, have you ever heard the description of what a mullet is?
No.
This is the front part in the back.
There you go, yes.
What?
No, but you gotta say like, business in the front, party in the back. That's a mullet. All right, anyway.
You give the ginger man
What?
I can't hear it.
Pick any 2 points on the surface of the cavity and find the line integral of the electric field between those 2 points. It's got to be 0. Why? Slightly different explanation than what I've got in the notes, but let's just do an alternative there. The line integral of the electric field between any 2 points on the surface of the cavity has to be 0 if there's no charge inside of it. Why?
Isn't that self-explanatory?
Well, how do you know? Well, no, why is it self? There's a important point. In fact, it's even true if there is a charge inside of it. But why is the line integral of the
Are
electric
we
field?
inside a conductor?
We're inside a conductor. Yeah, this is a conductor. All right. So I should draw a conductor. You know, my conductor should look more like this. There's a conductor. Okay, anyway. Line integral of the electric field is yes.
Thing status. Wouldn't it be because if you could move between 2 points on the conductor that had a non-zero, that would mean there's a potential between the two.
Mhm.
The charges would just scuttle around the intersection.
It's, we don't have to, so you could just stop it, there would be a potential difference between those 2 points, right? A conductor is an equipotential, right? This whole thing is at the same potential, right? And so therefore, the line integral of the electric field has to be 0 because it's an equipotential, which is, I can tell that's what you were going to say, yes or 2, right? Yeah, so.
Does it have to, does that mean the same thing as saying that the electric field is the same at both points?
No, you don't. You wouldn't say that because really the important point here is that the every point is at the same potential. So if I go and integrate the electric field between the 2 points, because the potential difference is minus the line integral of the electric field between the 2 points. So no matter how I go between the 2 points, I get a line integral of 0. Because otherwise, I'd be deducing that there was a potential difference. And so the argument here is then that Now I'm not happy with the argument suddenly, because if I put a charge inside there, this is still true that the line integral is equal to 0 between any 2 points, but there clearly is a field if there is a charge inside there. So suddenly I'm not happy with this. I was happy with it before, but then thinking about it. Because I was going to say, and so the only way this can work is if the electric field is 0 everywhere inside the hollow. But that's not true, because if I put a charge in there, there's no way the electric field is 0 inside that hollow, but it's still true. Yeah, like like there's a hollow inside the conductor, and then I just put a little point charge in there.
But I mean, like if that, right, as you go like across your path, like the potential could change inside and it just has to conduct the.
Right. Let's see.
So it's like delta V.
Yeah, certainly the inside of the hollow, if we put a charge in it, is not an equal potential. In other words, yeah, you're right, the potential changes from place to place. But you know, and this is one of the things, maybe I'll decide I'm wrong about this later, but I'm thinking that the author of the book makes a mistake here. Because the author kind of tries to argue here. The author is arguing that since the line integral of the electric field between any 2 points on the surface is 0, therefore the electric field has to be 0 everywhere in the conductor, everywhere in the hollow. But that isn't true. Again, because like Will said, well, if there's a charge in there, there is an electric field, so certainly there's a potential between those 2 points. There's a potential difference between those 2 points. There's still no potential difference between any 2 points on the conductor surface, but that's not the same as there's no potential difference between any 2 points. So really, to make this conclusion, we have to jump ahead and invoke this uniqueness theorem that we haven't proved yet, which is that if you've got a hollow here, there's no charge inside of it. If you've got a hollow and there's no charge inside of it, and every point on the surface is at the same potential, then one way to make that work would be to just assume that the electric field is 0 everywhere inside. That would certainly make it true that there was, line integral of the electric field was 0 between every 2 points. So if you just assume the potential is constant inside there, that there's no electric field, that works, and then since it works, it's the only possibility. Yes?
So when you say it's equal potential when there's no charge inside, so that means the surface isn't charged at all, right?
No, it could be. It could be. If I do have a charge inside
Well,
the
say
hollow.
like you don't have a charge,
If I don't have a charge,
then
that's right.
it's true because there's no electric field in the middle.
That's right. There's
But
no
once there
electric.
is a charge in there, the surface becomes charged.
That's correct.
Does that mean does that change it?
It still is true that it's an equipotential. The conductor is still an equipotential, even if I put a charge in here and there's
That's
an
what we just
induced.
had right there, right?
Mm-hmm, right.
So yeah.
Right, so every point on this surface, every point inside the conductor and on its inside and outside surfaces is all at the same potential. But that doesn't mean that there's no electric field inside this hollow volume right here. Certainly there is. I mean, if I get close to this charge, there's obviously going to be an electric field due to that charge there. If I can get arbitrarily close to it, good God, eventually it's going to dominate everything. Everything else in the system. Yes?
How do you know they're all the same potential?
A conductor?
Yeah.
Because we know that the electric field has to be 0 inside the conductor. Because, so, if we assume that there is such a thing as electrostatics with conductors, if we assume that you can have a situation where you don't have permanent electric currents flowing, because if you had charges in motion, you're not in an electrostatic, all the charges are sitting there situation. So if we can assume that you really can have electrostatics with conductors, that there is a configuration that works where all the charges are stationary in equilibrium, it has to be true that the electric field is 0 at every point inside the conductor, because a conductor is filled with charges that can flow. That's what a conductor is it's got free charges which are capable of flowing around inside of it. If there was an electric field inside here, any charge inside the conductor would respond to it and flow in response. So if we have achieved equilibrium, it has to be true that there's no currents flowing inside the conductor, and therefore there has to be no electric field inside the conductor. Do you buy into that argument? Does that make sense to you?
Is there any kind of mathematical thing that else to say?
That you could, it must be possible to prove this from the fact that, from Coulomb's law, from the fact that charges obey, the electric field of a charge is 1 over r squared, Q over 4 pi epsilon r squared. So there must be some way you could prove that. It's always possible to achieve that situation. But I'm not aware of how to do that myself. So I'm just kind of content to assume it can be done, basically. And if it can be, and if you can have electrostatics, it has to be possible to do that. If you can have electrostatics with conductors, it has to be possible to cancel out the electric field inside the conductor, because otherwise you violate the condition that we're assuming that it's a static situation. If there's electric currents, it's not electrostatics anymore because charges are moving. So assuming we can do that, if the electric field is 0, that means if I integrate the electric field on any path between any 2 points in the conductor, well, clearly the line integral of E dot dl is 0, so the potential difference between any 2 points I pick on or in the conductor has to be 0, and that's why it's an equipotential. If the field is 0 everywhere in some region, that region is all at the same potential, because the potential difference is the line integral of the electric field.
So, going back just a little bit, we were trying to formulate an argument for why there's no electric field.
Mm-hmm. Inside the cavity here, you mean, or inside the conductor?
And did we do that yet, or?
Did we do that?
Because you said his argument was flawed.
And yeah, that's what I'm thinking right now. This could be one, this is something where, I looked at my notes and I'm reading it, and all of a sudden I said, holy crap, I bought that when I was writing this, but now I don't all of a sudden. Because, the argument I have in the notes is, if there's no charges inside a cavity, E is 0 inside it, this follows from the fact that E dot dl integrated around any closed path is equal to 0, E inside the conductor is 0, and so therefore it has to be that the line integral from A to B for any path inside the conductor is also 0, but that's equivalent to what I'm saying here, that the surface is an equipotential, so this line integral is 0, but from that it doesn't follow that the electric field is 0. That's not enough.
What
Yes?
if you drew a Gaussian surface right inside the edge?
So
Just
I'm going
to,
like,
infinitesimal, yeah.
yeah.
And you know that since there's no charge in there,
Uh-huh.
there can be no net flux through the surface.
Right, that's true.
Now, if you drew another one just outside the edge,
Mhm.
on the inside of the edge,
Yeah, so then I'm going around
and by,
here.
and by definition, we know there can't be any flux through there.
Mm-hmm.
That, now, all this is net flux. You could have flux on both,
Right.
in and out. But in
Mhm.
order to have in and out, you'd have to have charges separated in that space between them, and then that would be an equipotential. That would violate our whole. So you can argue that there's no net, there's no.
You definitely know there's no charge on there.
Yeah.
That's certainly true. Because if there's no charge in here, any Gaussian around it doesn't enclose any charge, so there can't be any net charge on the surface. I'd have to think about it, but I think, and again, the author makes this argument and then kind of says, oh, and since any path this works, the electric field is 0. That's bullcrap. It's not true. It doesn't follow from that the electric field is 0 everywhere. And I think you do actually have to invoke the uniqueness theorem here. You have to say, well, if there's no charge in here, certainly one thing which would work that would make this happen for everything to be an equipotential is just to assume the potential is equal to the potential on the surface everywhere in here. It certainly works, if you just assume the electric field is 0 inside the cavity too, that gives you the condition that the potential is equal to the same thing everywhere on this surface and inside the surface. And then you invoke this uniqueness theorem which says, hey, if you can think of something that works, it's the only possibility. So I think that's actually the way that you have to go with this. Yeah.
See, that's what I don't understand, is if we're sitting here saying that there's a case we can think of where E might not be 0, how can you invoke this uniqueness theorem saying that, it's okay that one might not work? Because
No, but I'm saying it does work. I'm saying if there's no charge inside this cavity, if there is a charge inside this cavity, then the electric field isn't 0 inside the cavity.
But isn't that what we're trying to...
No, we're trying to show that if there's no charge, If there's no charge inside a cavity,
Okay.
then the electric field is zero inside
Okay,
the
well, I
cavity. That's what we're
understand
trying to
that
show.
I understand that one.
That's what we're
And I
trying to show.
wonder-
Yeah, if the charge isn't zero,
Or-
if there is a charge inside the cavity, then there definitely is an electric field inside that cavity.
Okay.
But if there's no charge inside the cavity, we're trying to show the electric field is zero inside the cavity. Yeah.
Answer that question.
So provisionally, that's my new argument, that in chapter 3, we're going to prove a uniqueness theorem that says if we can dream up a solution, it's the only possibility. And certainly one possibility that we could dream up is the electric field zero everywhere inside there. That certainly makes an equipotential. And it doesn't violate, if there's a charge in there, that obviously doesn't work, because if the electric field were zero everywhere inside the cavity, well, here's a Gaussian surface that encloses the charge, so there must be a flux through that surface. If the electric field was zero everywhere, there wouldn't be any flux through that surface. Gauss's law is violated, so that's not a solution. If there's a charge inside the cavity, that doesn't work. Then there is an electric field inside the cavity. But if there is no charge inside the cavity, I can draw any Gaussian surface I like inside there. There's no flux through it. And so that's perfectly consistent with the idea that the electric field is zero everywhere inside the cavity. So that works in the case that there's no charge inside the cavity. And then we say, yay, uniqueness theorem. If I dream up something that works, it's the only possibility. Okay, I dreamed up something that worked. I just assumed there was no electric field inside the cavity. That satisfied the boundary condition that the potential on the surface of the cavity is a constant. Happiness and joy. I'm done, because I thought of something that works, so that's it. And that's the actual argument. So, yeah, what the author said is wrong. I have to look at it again. Maybe I misinterpreted.
He actually did something different on here.
Oh, he did? Really?
I just looked at
Yeah, I
it.
guess maybe I'm just not remembering, and I just kind of, just made my own bull crap argument.
Plus on one side, minus on the other, and then specific closure.
Yeah.
Zero.
Mhm.
Yeah.
So we use our usual.
Right.
So,
Mhm.
it's zero.
Zero. But he says that.
Yeah.
You want?
Right, so he's saying if there is an electric field line, it has to go from a plus to a minus charge, okay?
There should be none.
But then there, yeah.
Solar.
Right, because the manifestly, yeah. Okay, so maybe the author isn't as bad as we thought he was, or as I thought he was. Yeah, he's deciding to put little charges on the surface of the cavity. Because electric fields would have to, because the electric fields end on positive and negative charges. So his argument was that this would have to be some plus charge right here and some minus charge right there.
If there's no Q inside?
If there's no Q inside, the only way for there to be an electric field inside would be if there was, in other words, all we proved so far is there's no net charge on this thing. If there's no Q inside, maybe there's still, it distributes itself with plus on one side, minus on the other, so there's still no net charge. If that were the case, then there'd be field lines connecting the plus and the minus charges to one another, and then there'd be definitely a line integral of the electric field between those 2 points. But wait a minute, it's an equipotential, therefore there can't be a line integral of the electric field between those 2 points. Therefore, there isn't any charge accumulated on the surface. But I still think it's true that to really complete the proof, you have to invoke the uniqueness theorem.
But he hasn't used the uniqueness theorem yet.
And he hasn't done it yet, that's right. So that would be kind of inconsistent, but whatever. We are going to prove the uniqueness theorem that would allow us to deduce this. So who cares? We've got it solved, and I have to think a little harder about that. But sorry, Griffiths, maybe you're right. In any case, it's time for a break. None of this breaking in the middle, because my pet peeve is broken chalk. Alrighty. Boundary conditions in electrostatics. And in particular, in other words, a boundary will be some surface that we're interested in. And that surface will have some local charge density sigma. Certainly doesn't have to be constant, does sigma. And what we're going to do is draw us a Gaussian surface which hugs the boundary, as it were. So in other words, it sticks out a little distance above and below that boundary surface there. So this usually goes by the name of a Gaussian pillbox, because it looks like a little pillbox, you know, contains your vitamins or your nerve medicine or whatever it is you have. And our Gaussian pillbox has area A. And, you know, as long as we're not at like a corner point, you know, like the vertex of a cone or the edge or a point on a cube or something like that, as long as you're not near a surface funky point like that, any surface you like locally is going to look like a flat surface, basically, if you get up close enough to it. So that's the idea, is we're considering a tiny, tiny, tiny little region of our surface, and our Gaussian pillbox is a tiny, tiny, tiny little Gaussian pillbox, which is hugging right next to a little small portion of surface, such that we can treat sigma as being constant over that tiny little portion of surface. And what we'll do is, we'll say, we want to talk about, say, the perpendicular component of the electric field above the surface. So I'll draw, that's supposed to be hovering in space just above the surface, the electric field, superscript perpendicular, subscript above. And meanwhile, below the surface, we have the perpendicular part of the electric field just below the surface, and above and below is up to you. What you call above and below is completely up to you. You can flip it around if you wanted to, but you know, if you're going to draw it like this, let's take above to be on top. That kind of makes sense. All right? So, the idea is that the thickness of the pillbox goes to 0. We're letting the top and bottom of the pillbox get arbitrarily close to the surface, so the thickness of the pillbox goes to 0, and what that's going to mean is no flux of E through the label, so to speak, of our pillbox, or through the, you know, if you think of it as a really squashed flat soup can, there's no flux through the label, no flux through, I don't know, what do you call that? I don't know that part, you know, whatever you want to call it. No flux of E through the side, which isn't the top or bottom. So the switob, the word of the day is switob, the side which isn't the top or bottom of our pillbox there. That's right, you can look that up in the dictionary and feel like an idiot when you don't find it. Okay, now, so all the flux is through the top and bottom surface. This is a tiny little pillbox, so the electric field can be taken to be constant over our tiny little pillbox. So the flux, in that case, is just going to be the area times the perpendicular component of E. Right? That's always true. The flux is just you add up the perpendicular component of E times the area over the entire surface. E dot dA is the perpendicular component of E multiplied by the area of the patch. So the flux through the top and bottom, well, the way we've drawn it here, and if you got a minus sign in a particular application, it just means the electric field is pointing opposite to your assumption. Flux through top and bottom well, that's just going to be perpendicular component of E above times A minus the perpendicular component of E below times A, because with our assumption about the direction of E, It's flux out of the top surface and flux into the bottom surface, and flux into a surface comes in with a minus sign. So it's E perpendicular above A minus E perpendicular below times A. So our buddy KF, who's KF? Yeah, right. KF stands for Carl Friedrich. Yes, our buddy Carl Friedrich says that total flux, E perpendicular above minus E perpendicular below times A is equal to the total charge enclosed divided by epsilon naught. And our little guy is so small, sigma is a constant, so therefore the charge enclosed is just the surface density times the area, sigma A divided by epsilon naught. Or, in other words, we've got an expression for how much the perpendicular component of the electric field changes as a result of a surface charge. Namely, the perpendicular component above minus the perpendicular component below is equal to sigma over epsilon naught, because the area canceled on both sides of that equation. And that's so important it gets a box thrown around it. Way. Way, Steph. Way. Okay? Do we have happiness and joy? Yeah. All right.
What we're gonna use this for.
What?
I said that's what we're gonna use this for.
It depends what we're going to use it for. We are going to use this to do problems in electrostatics. Let's see, what are we going to use it? Well, we will use it actually. And it will be happiness and joy inducing. I am confident of this. All right. Now, let's consider the parallel component. So this told us something about the perpendicular component of the electric field. Let's consider the parallel component. So I'll redraw my little surface here. Well, it's going to be my big surface. I'll redraw my surface, and this time, instead of a Gaussian pillbox, we'll make a little loopy guy. And so we're going to happily traipse around this little loop of length L that sticks into and out of the plane. So there's a little leg of it just above the surface, and then you dive down to the bottom side of the surface, walk just below the surface, and then you come back up again and you traipse around that loop. All right? You know, I like the word traipse, you know, traipse. I feel like I should have like a basket of daisies, you know, traipsing around, throw my daisies. That's right. Yes. Uh-huh. Oh boy, I'm taking the integral of e as I traipse around. All right. So, and now our picture will include the parallel component of E above and the parallel component of E below the plane. And we'll just arrange for our loop to be lined right up with the direction of the electric field above and below the plane there, although that's not crucial. It'd be easy to modify this otherwise. Okay? Now, this is an electrostatic field, and for every electrostatic field, we know that if we integrate round the closed loop E dot dl, that we get nada, because it's electrostatic field, so this would be finding the potential difference between a point and itself, which is certainly equal to 0, because you went around a closed loop. And so, if we shrink the sides of the loop perpendicular to the surface, they give no contribution, just like shrinking our pillbox so that the surface is laid just below the plane made no contribution to the flux as a result. So those little perpendicular segments don't contribute. And so what that means then is that E parallel above times L, that'll be the line integral above, because again, we're taking a tiny little loop here, so we can assume that the electric field is constant along that tiny little loop. And so then the line integral of the electric field dot dl just becomes electric field times L, if we've arranged to have the thing moving, or going in the same direction that E is parallel to the plane there. Again, if it's not, then you just put in a cosine of an angle to account for that, and that wouldn't really matter. So E parallel above times L minus E parallel below times L. Why is there a minus sign there when we go below the plane? Just because there should be. No? Yeah, so I've drawn it so that by assumption, I'm going in the direction of the electric field above the plane. But that means if I jump below the plane, I'm going opposite to my assumed direction of the parallel component of the electric field. So if I move opposite the direction of the vector that I'm doing the line integral of, that gives me a minus sign instead of a plus sign. So E parallel above times the length minus E parallel below times the length. Yeah.
I just had a question.
Yeah.
Are we just assuming this electric field is there, or is it the electric field from that surface?
It's the electric field due to the surface charge and everything else in the system.
Okay, so we're just saying it goes that direction.
Yeah, so we're just saying, that it goes that direction.
Okay.
We get out our handy-dandy electrometer and figure out the direction of the, or we take a little charge and let her go, and then, it's moving in the direction of the electric field, and so then we say, okay, we'll traipse our loop that way.
Okay.
Right? Yes. Okay? And again, well, it's okay if you didn't go in the direction of the electric field. You just have an angle between the electric field, and you just throw in a cosine theta, and that would cancel out in the end anyway. So this line integral has to add up to 0. Okay? Well, there's only one way that's going to work, and that is if E parallel above is equal to E parallel below, because factor out the L, divide through. So we conclude E parallel above equals E parallel below, EO, ELO. So in other words, what we've deduced is that the perpendicular component jumps at a surface charge, and the parallel component says, whatever, at a surface charge. It's continuous. The parallel component is continuous across a surface charge. No sudden jumps. It's continuous across any boundary. Whereas the perpendicular component jumps across the boundary proportional to sigma over epsilon naught. And often we call the parallel component the tangential component. So we often state that as the tangential component of E is continuous across any boundary. So let's make a single vector statement that contains what we've learned about both the parallel and the perpendicular components. We can do that by saying that the total electric field above minus the total electric field below is equal to sigma over epsilon naught times n hat, box around that one, where n hat is a unit vector, right? Hat always means unit vector. So n hat is a unit vector where n hat points from below to above. And obviously below and above are up to us, but if you change the direction, if you change the definition of above and below, that would just make n hat point in the opposite direction. But changing the definition of above and below would also change the order of these two vectors in the subtraction, which would flip their sign too. So in other words, as long as you pick a direction for n hat, you just say this is below and this is above, and be consistent with it, then you won't go wrong here. It'll give you the right result. So this is a perfectly objective statement of what's going on. Now, it's also one of those things where sometimes it's easier just to, instead of trying to figure that out, you just say, well, okay, I know from just what the sign of the charge is. So for example, at an electrical conductor's surface, we'll find that the local charge density is sigma over epsilon naught, and if the, if this is the conductor side of it, then if it's positive charge density, which way is the electric? The electric field inside the conductor is 0, right? The electric field in a conductor is 0. So the electric field outside, if the discontinuity is sigma over epsilon naught, and it's 0 inside, right? So we'll see now that this is true, okay? So if it's 0 inside and the perpendicular component jumps by sigma over epsilon naught at the boundary, then what's the electric field outside? Sigma over epsilon naught, okay. Which way does it point? Well, you could say, okay, we'll let this be below and this be above, so my n hat will point from below to above, and therefore blah, blah, blah. Yeah, but the easiest thing to do is say, this is positive charge. Which way does the electric field point? Up, right? It points away from positive charge. So in other words, don't bother with worrying about which way does n hat point and which one's above and blah, blah, blah. Often it's easiest just to say it's positive charge, so it's pointing away from positive charge. Or if it were negative charge, you'd say, oh, it's negative charge, so the electric field points towards negative charge. And you just do it that way rather than turn gymnastics worrying about the signs and all of that stuff right there. Okay? So that's one consequence of this, is that right up on the surface of a conductor, the electric field has to be sigma over epsilon naught, and it has to be perpendicular to the surface. We already deduced the electric field is perpendicular to a conductor's surface if it's electrostatics, because otherwise currents would be flowing along the surface in response to the parallel component of the electric field. And we could also deduce that the parallel component is 0 in another way from our conditions we've had. What would that argument be? How would our argument show that the parallel component of the electric field is 0 above and below the surface? Yeah?
If it wasn't 0, charge would be flowing in the conductor.
But that's what I said, that if it was, so that's legitimate, that works. But what about another argument? From our boundary conditions. How would you argue from the boundary conditions? What's the parallel component inside the conductor? 0. And what happens to the parallel component when you cross any boundary? Nothing. And so therefore, if it's 0 inside the conductor, what's it right outside the conductor? 0. So the parallel component also vanishes based on the boundary conditions. Same deal, you can get it either way. So the electric field at the surface of the conductor is in magnitude equal to sigma over epsilon naught, and it points outwards if it's positively charged and inwards if it's negatively charged at the surface of the conductor. Now, remember that if we talked about an infinite sheet of charge with charge density plus sigma, that we used Gauss's law and found that the electric field, how's the electric field vary in space above this thing? Hint, trick question. Does it vary in space? No, right? It's constant. And below it, it is also constant. Is it different above and below? Yes, from the standpoint of it points up above and points down below. The electric field is equal to what above that conductor? In magnitude, it's equal to
Sigma over epsilon.
not sigma over epsilon naught. Right, now we handy dandy do a quick Gauss's law calculation, right? You're always ready to whip out Gauss's law at a moment's notice. So we would draw our little cylinder that sticks above and below the plane, and we would say, here's area A, and by symmetry, the electric field's up everywhere. And so the flux through that surface is equal to well, yeah, okay, so it's equal to Q over epsilon naught, right? Okay. So what's the charge enclosed? No, it's sigma, right? It's charge density sigma, so the charge enclosed is sigma A. So sigma A over epsilon naught must be, bring in the electric field in the area here. Flux through the top surface of the electric field on that surface is magnitude E. What's the flux through that surface? EA, right? And what about through the sides? The label? 0, because it's aligned with the surface there. What about on the bottom? Is it the opposite direction? E is down. Which way is outwards down there? Down. So is it EA or minus EA? EA again. So EA plus EA is 2EA for the flux. So 2EA equals sigma A over epsilon naught. E is equal to sigma over 2 epsilon naught for a surface charge that's not got a conductor below it. It's just isolated surface charge. Memorize that. It's worth memorizing. You can quickly derive it, but you should know Coulomb's law, and that also should just be instantly, something that just comes instantly to your mind when you see a surface charge. So isolated surface charge, no conductor involved, just an insulator with charge density sigma. Electric field is sigma over 2 epsilon naught on both sides, right? Sigma over 2 epsilon naught down, and sigma over 2 epsilon naught up. How much does it jump by across the boundary? If I take up to be positive and down to be negative, then above minus below is sigma over 2 epsilon naught, and then I subtract the below side, but is the below side plus or minus? It's minus because we're taking up to be positive, so minus sigma over 2 epsilon naught for a grand total of sigma over epsilon naught. Is this consistent with what we deduced about the boundary conditions?
No.
Yes. This is a big piece of chalk. This is
I'll throw it back.
this is a javelin.
Oh my God.
Yeah, you'll throw it back. You've proven that. That's right. Yes.
And I will miss this time.
On God. You won't miss this time, right? Okay. So, consistent with what we learned, it jumps by sigma over epsilon naught. Okay. Now, I have big conductor. Big conductor.
Wow.
Yeah, all right. Little piece of big conductor. Whee! Okay, little piece right there of our big conductor.
Chad can definitely see that.
What?
Chad can definitely see that.
That's right, yes. Yeah.
He's ready for
Yeah.
his.
Magnified, okay, here's a magnified view. If you blow this up, it looks like this. Okay? Now, this little piece of the big conductor, suppose the charge density there is sigma. What's the electric field inside? 0. So just inside the surface, 0 electric field. What's the electric field just outside the surface? Sigma over epsilon naught. Right? Sigma over epsilon naught just outside the conductor. All right. Now, the total electric field should be equal to the electric field due to the charge. You know, I can draw a little patch around here, okay? So here's a little patch of the conductor. And so here's the electric field of sigma over epsilon naught just above that little patch. And I can think of it as being, all right, the total electric field is the electric field due to that little patch plus the electric field due to all the other charges in the system. Right, that makes sense. The total electric field is always the electric field due to all the charges in the system. And I'm always allowed to break the charges in the system into little part of the system 1 and everything else in the system. So the total electric field is the electric field due to the little patch plus the electric field due to everything else. Okay? If I'm very close to that little patch, does it not, if I get close enough to it, look like an infinite plane? No matter how small the little patch is, I can always get so close to it that, you know, I'm within 1/1,000,000th of the diameter of the patch. No matter, and again, you know, I mean, in reality, charges are discrete, they're quantized, little electrons or whatever. But here we're treating everything as continuous charge distribution. All right. So no matter how little I make my patch, I can get so close to it that I'm, you know, like that the patch looks like an infinite plane to me. Does that make sense?
Yes.
All right. So the field of the patch itself then should be equal to what? So in other words, what I'm kind of saying is the total electric field, patch, and everything else, all the other charge on the conductor, in other words, all the other surface charge on the conductor, patch plus everything else. Well, the patch by itself should give what for the electric field just above and just below it? If the patch looks like an infinite plane, if I get close enough to it, okay, now this blackboard looks like an infinite blackboard to me. Wow. This is amazing. I'm losing my breath thinking about it. I'm making a little voice cloud on the board. All right. Water. I need water. It's empty. All right. Okay. The patch by itself should produce what electric field just above it? Sigma over 2 epsilon naught, right? So this is supposed to be half as big. Sigma over 2 epsilon naught just below it, just above it. What about just below it? Well, yes, sigma over 2 epsilon naught pointing in what direction? Into the conductor in this case, right? So then there's also sigma over 2 epsilon naught into the conductor. And then if everything else added to this is supposed to give this, right, the net electric field, 0 below, sigma over epsilon naught above, if everything else added to this is to give this, then everything else contributes what? Just below and above the patch. Yeah, it contributes sigma over 2 epsilon naught. Okay, I'm getting myself in. Yeah, which direction, right? Up or down? Up, yeah. Sigma over 2 epsilon naught, I'm happy again. Sigma over 2 epsilon naught just above the patch. What about just below the patch? Up or down?
Wait, I don't know.
So above the patch, this plus this adds up to this. That works, right?
Above.
Sigma over 2 epsilon naught up plus sigma over 2 epsilon naught up equals sigma over epsilon naught. So now, what plus sigma over 2 epsilon naught down gives 0? Sigma over 2 epsilon naught up. So in other words, at the location of the patch, all the other charge in the system is producing sigma over epsilon naught, both above and below the location of the patch. The patch itself is and it's up. The patch itself, if the patch is positively charged, the patch itself